going to be able to start from tomorrow morning, but I hope that's okay. So yeah, actually, welcome to the second exercise, and yeah, that's indeed like the very first thing we're going to talk about in today's session, which is managing file path in Python. So I looked a bit at the GeoPython material, and it turns out mostly there you would work just with like a long string that would have the entire file path. And there's different ways of dealing with file path in Python. The historical one is like just long strings, really often with like an R before defining it, which means raw. So you can use any character in this string. However, that has a few problems, especially if you work sometimes on your computer, sometimes in, say, a notebook interface, or sometimes on some virtual machine, sometimes on a Mac, sometimes on Windows. You share code with your colleagues. So you automatically run into some problems there with like two things. Like one is like absolute file paths are not the same. So if your username is, yeah, your username on Windows is c:\users\username, kind of, that's your home directory on Windows, and then on Linux or on Linux it's /home/username. On Mac it's /users/username, I think. And then on these online platforms in the cloud, it's usually something completely random that you don't have any influence on. So on our notebooks, for example, it's /home/ something with Jupiter. So the Latin name so Jovus is Jupiter, but it's like Jovians or something like that. So anyway, like you don't always have a control over it, and we already touched also, like I mentioned that really quickly in here, that on Windows you have the backslash, on Linux and Mac OS you have the / as a divider between directories. So it's really quickly quite a mess. So and there's been these libraries or these module OS and OS path, which has been used a lot to manage file path. But then since about 3 years, there's this new module in the Python core libraries that's called pathlib. And pathlib is really great. And so this was now the introduction. And I said pathlib is really great, and we should try it out. So for that, let's go again to the notebooks. And there should be, yeah, if they start, but please, everybody start your notebooks too at the same time. And I wonder what's up with mine. Yes. And go into the Automating GIS-processes notebook. And as always, once you started it, you already have the notebooks directory, and it should already have for the lesson 2 already some notebooks too. If you're already there, then open this managing file path notebook. So inside notebooks, lessons, lesson 2, there's this managing file path notebook. Is my screen large enough? Can you see the screen? No, let's try to make it bigger. Hey, like somehow this Jupyter notebook doesn't. Oh, no, good. No, it's too big. But anyway, we're going to use this pathlib, and pathlib is, as the name in a way says, a library to deal with file path. So and it's called pathlib. So if you just import pathlib, we have all the functionality there, and then let's create like the one important thing in the whole, the one important class in this entire library is the path. So if we create a pathlib path, let's put it into variables straight away. And if we create it without any argument here, then it would point to the current directory. So if I now print it also, then you would see, yeah, dot is the current directory. And yeah, interesting to have the dot in a way, but that's very local. So you kind of like this pathlib module, this library hasn't even checked where is the dot yet. So, but it just like took it kind of, oh, you told me to create a path, and we take the default is where we are at the moment. And it's very handy because this is where the notebook is. So this like it knows this is where we are right now. The file I'm running from is the current directory. It doesn't help a lot if you now want to open files and you want to open that file maybe from somewhere else. So the most handy first function of this path is to resolve it. And then if you resolve a path, oh yeah, that's the word I was searching for, Jovian. Then it would figure out this dot directory, where is it actually, and in this case on the libraries on this CC notebook system, the dot path of this particular notebook is in this directory. So it's in home, Jovian, notebooks, lessons, lesson 2. And this note actually is is here because this is the same notebook that is also on the like the source code for the website, for the course website. So on the course website, if you compare that, this path would be completely different because it's being generated on this read the docs web page, and it has, yeah, it's much longer and it's much more complicated. But that's exactly the beauty about this. You don't have to care in the code about how your home directory actually looks like or where it is, but it would, or home directory, just current directory of the file. So pathlib path resolve would always give you the full directory name of where you currently are. And this is now a POSIX path object, but this does not really matter. So most functions that open a file can just accept this one, even if they actually want a string. So you just pass in this path, and it would work by itself. So it would convert itself into a string. And then this path is not just this string that points somewhere, but it also has a lot of functionality. So you can, for example, see whether the path exists, or you can also check whether this path is a directory. And I did not put that link in here now, or at least I don't see it. But as a, no, that's wrong. As a quick peek preview, the documentation of the Python built-in library is really good. So you can just go here to docs.python.org, then go to library, and then choose the pathlib. And there's a whole, no, where is it actually? There's a whole list of properties and methods that these paths then have. So you can get the stem, for example, which is the last part of the file, except like the file name itself, except the extension. You can get just the extension. You can figure out whether a path is relative to another path, that it means like it's inside like a directory, for example. You can join it with another path. You can match it against a pattern. A lot of these, and we're not going to go into details on those because we only have 1.5 hours. You can also use, like, for example, this rename it to kind of rename the directory, for example, in this case, or then delete it, but these are commented out because otherwise we couldn't continue with our lesson now if we just delete the current directory. And then what I personally find the most beautiful part about this is that you can just combine it with additional components of the path, and you would just use this normal slash, so kind of division operator, and combine it with, like, for example, another directory name that's underneath it. So this would, okay. But I know, yeah, sorry, I forgot to like actually save this resolved path inside the path. So if it's resolved, then this would give me also the absolute path of data. And the other way around, if you want to have like one directory higher up, you would use this parent. So like it would go one directory up. And yeah, there's still this one. It's a very good habit to define, like when you have this long notebook or long script, to define your data directory or the base directory of all of your data at the very top, so you can always kind of use that variable then in the code and know this is pointing to my data directory. And like that would, in our case, for example, this is like the directory where this file is in for this session. Resolve it, so it's an absolute path, and then /data. So this is where our data is stored for this session. I hope it's stored in there, to be honest, but I think it is. Let's see. And I would store that in a constant, and a constant does not really exist in Python, but there's convention around using that. So constant as such is, it's just like a variable, except that you agree on never changing it. Like in other languages, you cannot actually change it. So it's like once you define it, it's staying the same. In Python, it's more that you kind of have a convention that if you write a variable name in uppercase letters, in capital letters only, then this is something that never changes. So once it's defined, you just don't touch it anymore. So you know throughout your script it has that value. So you can rely on it. It's not so important if you have these, like, I don't know, the short notebooks, but if you start to have larger projects, maybe sharing constants across different notebooks by importing them from other places, then it becomes really important that you kind of stick to these conventions and not touch the things. Like once we have this data directory now defined, we can quickly show how to use that. So we're gonna later, like just after this, work with GeoPandas, which is a library to load geodata, and I'm gonna give you a peek preview here now already of this GeoPandas read file. Is to open different file formats, and here you can just use the data directory and slash again to combine with like a file name, for example, or a different path. And I can tell you that we have a file in here that's in a subdirectory of there, which is called Finland municipalities, and then within that subdirectory it's called Finland municipalities underscore 2021.gpkg, so geo package file format. And that would be, if I can type this, so we would load the data into this municipalities variable, and then let's just, to show that it actually loads, let's already have another peek preview and plot it. So if you run this, okay, there's some problem with like some error here, but it still works. So this now loaded this Finland municipalities file, and I can show you quickly. It's in here, like in data, Finland municipalities, there's this file. And we just loaded that one and plotted it. And it's the municipalities of Finland, surprise, surprise. Yeah, that's kind of how to manage file path most efficiently or most robustly also, so you can move it from one computer to another using this pathlib library. Any questions so far before we move on? It can also be like, I don't know, why the hell are we supposed to use such a complicated thing when we can just always hard code the path? And the answer would be, yeah, you can always hard code the path, but then you might have to change it in 7 different places once you move to your colleague's computer. Okay. But otherwise we would move on and check out this vector data notebook now. So it's vector data input output. And maybe we can take a second still and can you, everybody for yourself, quickly think whether you know what a shapefile is, what a geo package is, what a coordinate reference system is, what a datum is, and what EPSG might stand for? I don't expect all of you to know all of these, and just let's take a minute to just go through the list and think whether you know what things are, and then we're gonna solve the riddle. So how many, like, just show me with your hand, how many know what a shapefile is? Great, everybody, perfect, yes. So a shapefile is a vector dataset format that was defined in the 70s, I think, or at least 80s, really long ago, by Esri, like the company behind ArcGIS. And it's also a bit of it's kind of the tested and tried data format for geospatial vector data, but then it also has its very own problems. So it has some limitations just because it's very old. For example, text attributes can't be longer than 255 characters, which sometimes is a problem, sometimes not. And it's prone to, because it's actually not one file, but it's up to seven files. It's also prone to kind of be messed up when you copy one file to another place. That's why there's a geo package, which is a standard that has been defined maybe 10 years ago, I'm not 100% sure, by the Open Geospatial Consortium, which is a vector file format container that kind of tries to combat those problems. And it's open, so it should be adopted eventually by many places. Shapefiles are still around, and shapefiles are still gonna remain the standard file format in many applications, but you see more and more geo packages around. Then a coordinate reference system is, we're gonna go there in, like, after, maybe at the end of this session, if we have time though. It's in a way a mathematical function that describes how a point on three-dimensional sphere of Earth relates to a point in a two-dimensional map. So that's kind of it. It also defines the unit of measurement, so whether it's meters, for example, or degrees, and it's kind of always optimized for a certain purpose. Datum is part of the coordinate reference system. It defines what kind of ellipsoid, whether it's a perfect sphere or a bit of a potato-shaped Earth that we talk about. It defines where is the center point, whether it's always Greenwich in London or the equator, and you can change all of these. And there again, like the potato shape can be optimized for different places around the world. And then finally, EPSG is this database of different map projections and coordinate reference systems where you can use, for example, 4 to 6 digit number to define this or to reference a certain certain reference system. So the most common one is this 4326, which is the WGS-84, which we all know as latitude, longitude, degree, position. So if you anywhere have like this, I don't know, Finland, Helsinki is at 60° north. That's most likely in EPSG 43. But let's try the vector data input output. So yeah, like we talked about, there's shapefile, there's geopackage, there's a million other formats, and you probably had struggled with those before. The good news is geopackage and Python in general has a library to open anything, like almost. There's probably edge cases where you have problems, but you're not gonna come across those. And yeah, first, before we do anything else, let's do this. What I just suggested, to at the top of the notebook define a notebook directory, and that's in the notebook, so you don't have to copy and paste. You just have to run the cell, and then it would see like where's the notebook itself, and define the data directory as like the data underneath notebook, underneath the notebook directory. Let's first check this Fiona library, which I can tell you is behind, is working under the hood of GeoPandas. It can show what kind of file formats it can read and write. And like it has this, like if you import Fiona and then print this Fiona dot supported underscore drivers, it would give you a long list, and there's the error again, so I have to look into that. This is not such a long list, but that's probably because we're working in the notebook, but still you have all the usual suspects of geospatial data files. So shapefile is here, geopackage is here, GML is here, GeoJSON is here, GPX, like so GPS track files, map info, like an old GIS or traditional GIS package, SQLite, TopoJSON, so kind of pretty much everything here. And like these codes behind it say, like tell whether you can read or write the data with this package, or whether you can even append to an existing data set. So this is kind of just to demonstrate you're not gonna easily find files that you cannot open with GeoPandas. And let's do again what we already did, like quickly, and do it more thoroughly. Let's look at how a data file looks like if we open it with GeoPandas. For that, we have to again import GeoPandas, and then how did I call that here so we don't not run into problems? Oh yeah, it's again the municipalities. So we again use this read file, and again it's inside data directories. There's a directory that's called Finland municipalities, and inside there's a file that's called Finland municipalities underscore 2021.jpkg, and I hope this line breaks when I hit enter, so you can still read it. So I'm gonna try whether it stays here. If it doesn't, no, of course it doesn't. So I can scroll here still. Did everybody catch it? So, and let's look at how this file looks like. Or the data set that I just read from here. So we imported that, and then, yeah, doesn't that look really familiar from GeoPython? So the good thing is GeoPandas, and I mean, it's in the name, it's the geographically enabled pandas. So you can use all the skills you learned in GeoPython to manipulate pandas data frames, also on these GeoPandas geo data frames. They're really called that way. And the only difference here, and this is just a bit, I have to zoom out a bit, otherwise I can't move. The only difference here is that there's an additional column that has a geometry, and inside this geometry there's what in fact is a shapely geometry object. So what we used in the exercise 1 and the last lesson. So in a way, we now have brought together all of GeoPython and then lesson 1 of this course to form this data frame that is geospatially enabled and has the geometries here. But let's maybe still go forward and check something bit interesting to show how much of a Swiss pocket knife this tool GeoPandas actually is. So if, like, I'm just gonna show you quickly. Sorry, I'm typing and talking at the same time, and I seem to not manage to be able to do that. So what's interesting is GeoPandas is so kind of ingeniously written that you can just I'm going to copy this from over here. I'm sorry, I'm too lazy to type it. And you can also copy it from this Vector.io data notebook over here. So you can just take this entire address from over here and if you look closely, this is actually not even the geodata itself, but it's zipped inside an archive, and it's coming from an European Commission website, and it would just be able to open that straight like that, and you wouldn't have to have local file for that at all. Although the European Commission is going to call me tomorrow that why I made 30 people do the same download at the same time and 7 times after another, but yeah, like the functionality is there to just open from anywhere. And yeah, we're going very fast here. I realize, but we unfortunately don't have so much time today, and we have quite a lot to learn, or quite a lot to see. You know, like all of these things come naturally once you've heard them once. So let's try already to save data again. So we now open this European Commission file from the internet, and so if we want to reuse it ourselves locally and not always open it up from the internet, we can also write that to a file, and I call this nuts regions. The geodata frame, but it has this handy method to file. It's really similar again like the read file, and both of them are really similar to Pandas read CSV and to CSV. So they work exactly the same way, except that GeoPandas to file and read file are called file because they can read many different file formats, while Pandas can like each method of Pandas only can read one file format. So we could now, for example, again use this data directory and save it to and let's choose a different data format to demonstrate that this to file can do everything. And I'm now choosing GeoJSON, which is like this, you know, internet enabled JavaScript optimized geodata format. And if I run that and check from the files here, and this is then I just wrote seconds ago this new file. And it didn't take long at all. Then there's a short part here which you can't try, but which is here as an example, and you can maybe check that at home. It won't work at home either if you don't have a database lying around, but like GeoPandas can also read and write to, for example, PostgreSQL databases. It's all kind of built in, but yeah, it's a bit more complicated, and it goes maybe beyond this course to actually do that. But there's the hint here. It's not very complicated, so you still only need like these 10 lines of code to get data out of a database table or save it. So like 10 lines for getting it out and saving it. And again, it's like read PostGIS and to PostGIS, so the syntax is very similar. And then finally, and that's again something where I'm going to be lazy and copy and paste, you can use this read file also with a WFS endpoint address. And why I copy and paste that is because writing this endpoint address it's a bit manual, but you can also just copy it from, for example, in QGIS, if you open the layer properties in like it of a WFS layer, it would show you this address, and you could copy and paste it into there. But yeah, what I do here now is like from this HSU karttapalvelu, so from the map services of the, what is HSU, the utility company of the Helsinki region. From their server, we load a layer that's called it's in the category living and land use, and it's the population grids for 2020. And I also told it to only get this like small extent, and yeah, this is part of the web address, and it's a bit complicated, but this is just to demonstrate that this works directly too. And the best bet is to open the layer in QGIS and copy the address from there. And then you get the raw data here. Again, how do I, sorry for zooming out here again, but just to show you there's all of the columns, like in a pandas data frame, and then the geometry on the side. So that's, are we kind in time? Yes, we have half an hour on 45 minutes even left to actually do something with data. So now we've learned how to manage file paths in an efficient way. And we've also learned how GeoPandas can open different file formats as a data frame, which also has geometry attached. But we haven't really seen a lot of what you can do with it then. So let's go back to open the third notebook in our folder. And again, there's a lot of things. Yeah, sorry.
Can you write a data frame to any file format, or does it have to match the file format of the one you loaded?
No, it doesn't have to. Like you can choose any file format. So the data frame itself is kind of, it's not coupled to the source file. It's standing on its own. So it's yeah, you can write it to any file format. I mean, granted that GeoPandas supports writing to that file format, but I mean, yeah, beyond that, yes. So a lot of things I already said in the first two places here, and this one is here to just run it. It loads like a shape file out of a data directory file, but it's just to show that there's like this geometry column, and we already talked about that. So it's a normal data frame, has all the attributes, and then a geometry column. Let's look at actually exploring and analyzing and regrouping like a more complicated file here. So first thing, again, like I defined this data directory path, and you also have that copy and pasted already in your notebook. So we have an easier way of finding the files. And we're gonna There's something missing in here, which hopefully is over here. Yes, and like we're going to work with this Finnish topographic database, which is created and updated and maintained by the Maanmittauslaitos, the National Land Survey of the country. And they have this topographic database which kind of contains everything. So from roads to land use to points of interest to houses to, yeah, land cover. Did I say that already? Anyway, like pretty much anything is inside this database, and it's freely available for download from this Baitoli geodata place. And nowadays you can get it as a geo package for the entire country, but when this exercise was written a couple of years ago, it only came in these shape files for little boxes, grid cells throughout the country. So it's a perfect example of if you want to have coverage of more than just one grid cell, you might want to use something like GeoPandas to put things together. And yes, then this already exists again over here. So we defined the directory, and then maybe quick description of the data that's in, like we want to, like the task we want to now do inside this next 20 minutes or something is we want to take all the terrain features, and there's a long list of them. So there's, for example, motor traffic area, then there's garden, then there's earth field, there's sports area, and there's lakes. We want to take all of them that are in the same file and output separate files for each of these classes. And I mean, there's, I don't know, 30-ish classes of this somehow. So it would be quite a lot of work to do that manually. And so it's a really good task for exploring how to use GeoPandas and scripting. And we're going to, for finding the files that are relevant for us, and I can already tell you, like from having read the file naming convention in the metadata of the Baitoli dataset, that the files we want, like where terrain data is in, start with the letter P and end, start with letter M and end with the letter P. So and to search for all of them, we can use this matching function, which is off the path. So like every path we define, for example, data directory, has this method glob, which accepts a search string that describes the file name. So for example, *.shp, the asterisk would be replaced by any character that's in the file name, so it would list all shape files. And we can use that a bit more complicated and or a bit more advanced. Let's maybe first define like a nicer path, because we're going to be using this topographic database quite a lot, and we know it's inside the data directory in the subdirectory Finland topographic database. This is just so it's easier to use it again. So like we don't always have to type out this entire thing, but we can just use that one. And I'm going to copy that down here and then use this glob. And did I say, like, yeah, it starts with an M, then there can be whatever characters, the asterisk. I can make it a bit bigger again, because I think we don't need the full width of the display now. And it ends with a P and then .shp. So those are the files that we want. And like if I run that now, it's again like a generator or iterator, which is something we haven't covered yet. So let's quickly just convert it into list using list in the front, and then we get the list of only one file. So in this data set, because we only have the one grid cell of this entire topographic data set, topographic database, our dataset only has one file that matches our file pattern. But you can get a whole list. So if you have an entire directory with many subdirectories with like the different downloaded files, you can use glob, for example, to find all the files that are this. So because we only have one, that's irritating. I'm just copying it down here and say that the first one, like index 0 of the list, is the file we want. So this is our input file. Did I call that input file over here? Yes, good. So let's look how that actually looks like. So and we have to first import GeoPandas for using it. And then we can use, again, this GeoPandas read file of this input file. And let's maybe print how the input file looks like. So you see it's like this path, and it's pointing to this particular shapefile inside this long directory. And yeah, let's load that. And it went really quickly. And let's also check what type, or what data structure type it is. And it's a GeoPandas geodata frame, which is exactly what we want. So maybe you can do this next step on your own. Do you remember, or I hope you remember, from GeoPython how to print the first few rows of a data frame, and how to list the column names or the columns of the data frame? And let's try whether the pandas functionality also works with GeoPandas. How are you feeling? Did you figure out how it works? Mm-hmm. So like maybe I'm typing that in here still too. So it's this .head method to show the first few rows of a data set. And because I'm zoomed in so much, you can't really see that, but yeah, 5 rows and 39 columns. And then the .columns property lists like what kind of columns there are available. And yeah, well, this is a Finnish data set, so not all of you speak Finnish. My Finnish is also very broken. So it might be a good idea to like get rid of many of those columns, because we don't really need them, or not for our exercise today. And also translate some of the names. So we want to keep the geometry column. That's really important because that's our geodata. And we want to keep the ryhmä and the luokka. So ryhmä being group and luokka being class in English, which is the classification of the terrain items. So do you remember how to, I'm not sure whether that has been covered in GeoPython, but probably it has. Do you remember how to rename a column in a data frame? Maybe you haven't covered it. That might well be.
No, it was there.
It was there? I can still just tell you also. So, was there something else to do here still? Oh yeah, first let's get rid of all the other columns. So let's redefine the data as like this subset of data that only has what did we say? Ryhmä, luokka, and the geometry columns. And then the renaming works by using rename method, and the rename method accepts this dictionary where the keys are the original name. So I would say, for example, Ryshma is the key of here, and the value that's associated to the key is the new name. So I would now type, for example, group, and the same for the Luokka would become class. And we leave the geometry at what it was. So this would, like, yeah. And I forgot something because we still have to tell data what we want to rename, and it's the columns. You can do the same with rows and maybe something else still too, I'm not sure. And if I run that and show the data now, then we have a column called group, a column called class, and the geometry, and 4,304 rows. So there's then again like a quick exercise you can do yourselves, please, except that this is now a bit messed up, so maybe do it up here above this box, because there's no gap in here. Can you so like by adding a new, no, how do you add a new thing with the mouse, a new box?
I'm getting an error while
Yes.
renaming it.
Mm-hmm. What error do you get?
It says that this object has no attribute to rename.
Did you already? Is data like, did you call your data frame data, or did you call it something else?
Oh, it's data.
Looks like, can you run all the cells above and then check? And everybody else in the meantime, could you try to find out what was it in this info box? The number of rows, I think, was like 3 items, but there's this green box in where we just were. I mean, yeah, you forgot here like the data here, but you can just like then like run all until here, so things again AR. Has it run now? Yes, great. So can you then also try to find out how many rows does the data set have? How many unique values are there in the class column, and how many unique values are in the group column? And I'm gonna give you a head start of a minute or so, and then also start typing the solution. What did I ask? How many? Okay. So I got the most straightforward, shortest solutions here. There's always so many solutions, so there's hardly ever like a time that some code that works is actually wrong. I mean, there is occasions of that, but usually there's so many versions of different ways to come to the same solution. What I now did is I checked the length of the data frame, which gives me the number of rows, which is 4,304. And then I used this n, like number of unique values method of the data series. So I use this data class and then number of unique. And it tells me that there's 21 classes and one group inside this data set. But now let's do something more fun, like not counting numbers. I mean, that's also fun, but different kind of fun. Let's make a map. And creating a map is again, like it's really similar to pandas. If you want to explore a pandas data set, you would plot a chart to see, I don't know, like for example, bar chart, depending on what kind of data you have. And GeoPandas just plots into a map because it knows that it has geometries. So it would look like that. And in the exercise, it says people living in the Helsinki region might recognize some of the shapes. And I have a hard time. This one is a lake, isn't it? So, but does anybody know where that is? Yeah.
That's a bit better there in this spot.
Ah.
There's like room there to the left of it.
That one.
The large one, yeah.
Yeah. So this one is then Nuuksio already. Yeah. Yeah, so we have the clearly geometric objects in there, geometry objects, and let's take a closer look at those, because and this is again something which I do so naturally and then never explain. Like you know that you probably covered that in GeoPython, but I don't know, it can't be repeated enough. So if you have a data frame, you can access the different columns in at least two different ways. So you can either treat it as like kind of members of a list and access it like an attribute, or you can, if the column is defined already, you can also use a dot and treat it as a class property, and it's exactly the same. It just looks different. One has advantages in one way, the other one has advantages in others. So it's a bit of a matter of taste if you can use both. Sometimes you have to use one particular one, but most of the time you can just use either one. But yeah, let's check out the geometry column, and you can see how it's, I already told you, it's shapely geometry objects, and they're being printed here again as well-known text. So in this human readable with big quotation marks, but still human readable form of, like Polygon, for example, has like this multiple rings inside. So like it's in parentheses, these are the coordinates of the external ring, the first view that we see here. And those are shapely geometries. So you can use all of the things we used with shapely geometries, like in the last session. Let's first take maybe only the very first item in this list, and I'm not 100% sure whether this has been covered in GeoPython, but to get like one single value in a data frame, you can say you can use this at method. So you would in the 0th row in the column geometry, you want to have the value that's there. And if we do that, then we find out that there's some oddly shaped polygon in there. So it's being drawn here. So this is the value of, if we print it, then we have the source code of the polygon. But if in Jupyter Notebook we just output it, then it's being drawn. We had that last week too, like that the dots would be, and the line strings would be drawn. And we didn't go to the polygons, and we're gonna cover that today. And similarly, we can also use this. So this is like the very first, the geometry in the very first row. We could also say here like in row 56, and then it's another one. And I don't know, let's see the geometry in row 56. We can also use all of the things we did with shapely geometry. So we could, for example, check what its area is. And I'm gonna make this a bit nicer. So, and calculate it into a variable, and then print it with like an f string and say the area of the polygon in row, what was it, 56 is And now, unlike last week, I can actually say it is square meters what the area is, and we're gonna come to that in a second. Not sure whether you've talked about these in GeoPython. Yes, good. So like how to form, like if you have a variable name inside an f string and you put a colon there, and then you can still add like the formatting string, how it should be called, how it should be formatted. So I want to have one digit after the comma. And I know it's square meters. And why do I know it's square meters? Because GeoPandas carries over the coordinate reference system. So I know that this is a coordinate. I can tell you now, but we're gonna explore it ourselves in a minute. I know this coordinate reference system is in meters, so the area is in square meters. Now, this is of course a bit boring if we have to go through all of them like by hand and always change here the numbers, and kind of it's the same value almost. So let's look at the real power of GeoPandas, which is you can do that for the entire data frame. So you can just use this dot area on the entire data frame, and then you will get the area calculated for each row. Okay, we skipped now one cell in here, but if you're very interested in how to use the iter rows, which we have covered very often in GeoPython, then you can revisit the file on the course web page. And of course, we can also create a new column called area, which has the, oh, sorry, that's wrong. Which has the area of every item. So it would assign to a new column called area the results of calculating the area for the entire data frame. So it would per row create one area and then put all of these into a new column called area. So like together it then looks like that. We still have the existing group and class column geometry, and then I just added this area, which has the value of the area. And do we have time for this? Yes, we do. So again, like a 2-minute exercise for everyone yourselves. Now that we have this area column, and I hope everybody has that, can I clear this output? Yes, so you can see it better. So if if you create a new area column and have then the area there, can you quickly find out what's the smallest, what's the largest, and what's the average area of these geometries, and what's the sum of all the areas? And there's also standard deviation here, which is kind of the optional, the bonus point here. Okay. And of course, the standard deviation doesn't make much sense by itself without having a median also. So yeah, like I guess everybody already got the system of it, and you saw also that I didn't remember exactly how the standard deviation function, standard deviation method worked, or what it was called exactly, but you can always look it up. But the idea is that you can, for each of these series of the columns, you can just use these methods which show you descriptive statistics about it, like maximum, minimum values, the sum of all of them, the average, like the mean average, the standard deviation, or the median, for example. There's so many more, but that really then is whatever you need for your particular problem. So let's still do something else. So like if we now say we want only the lakes inside this terrain dataset, let's filter that from the data. So like you say, we only want data where in those rows where the data class is 36,200, and I've written that here in the notebook itself, but it's actually taken from the table we looked at before. And let's maybe also list the lakes straight away. And we get them like, yeah, we get like, I don't know, a few of them. Wow. Okay, I should not have listed them. And we can again also use this lakes plot function. And then it's even more clear, like, yeah, Pitkäjärvi bottom. Okay. And is that one then like near the National Park house?
I think so.
And these are on Wichtindee that goes somehow like through here. Interesting. I wouldn't have guessed that myself, but now that you pointed it out, kind of find myself in there. And so we have the lakes here now, and we can of course just save the lakes. So we can say lakes to a file, and again inside this data directory, for example, lakes.shape. But because you you can just choose any file format. You can also write to lakes geo package, and for all the usual files, it's like GeoPandas guesses from the file extension. So you can still set it with like you can still fine tune it, and you can check the documentation for this GeoPandas to file method, and it would tell you how you can, for example, into a geo package, you can save multiple layers into the same file. Then you can still add here that the layer should be called, I don't know, like something else, but yeah, like just the basic syntax is just like choose the file extension to name to choose which file format it should be. And then one more thing inside this GeoPackage section is grouping data. And you have been working with group data in GeoPython. I know that for a fact because I was there for that particular session. But let's do that on the geodata frame, because it's almost the same, but of course it offers a few more possibilities because we have geodata suddenly. So let's check again, just as a reminder, how our data file looks like. So we have the group and the class and the geometry, and then we also calculate the area column at some point. So with data.head, we see kind of how it looks like. And then we already use this number of unique method to find out how many different classes we have. But let's check how the classes actually, like what their values are, the names. So we can also use this just unique without the n, without the number. It would print, oh no, yeah, this is a column that doesn't exist. So, and we see that there's like these 21 classes. And I guess you have been using this group by function, but it also works here. So let's check how we can group the data into, like by, for example, this class column. So we would end up with like 21 different groups of values of records of geometries that relate to each of the classes. And let's also still output that here. So it tells us it's like this group by object. So it's not the data frame itself, it's like a wrapper around it. And just this is a bit showing what's happening under the hood, so you don't really have to remember that, but maybe it's good to see how things work. So this group data, this group by object kind of has this inside itself, it has this lookup table kind of thing. So it would remember in this dictionary that like for the class, like the class 32,111 has like these or this one item that belongs to it. Then, for example, there like this 32,611 has like actually a lot of rows that belong to it. So it's kind of, it's more of a wrapper around the data frame that tells if we group it by classes, that's the rows that belong to each class. And that's a very long thing. So and then yeah, we can also iterate over this group by. So we can and it gives you always the key and then the list and then the not this list, but actually the rows that belong to it. So like we would, for example, in a for loop, we could say for key and group in like this grouped data object that we have. And so terrain class, what was it, key. Let's just use it quickly to count how much is in there. kind of loop over all keys and all the data that's in there, all the groups, and you would see that there's, for example, what was our lake? Yes, it was this one. So like 36,200 has 56 polygons, so we have 56 lake objects inside that. And finally, there's also this get group. So if we have the grouped, but I have to be honest, I've never used that before. Somehow there was always something else that was more handy. So if you want, for example, to get all the lakes, we could use this get group and the code for the lake class, and it would return everything that belongs to lakes. And it's these 56. And yeah, and as you can see, that's kind of quick caution note here, because as you can see, it does not start to count from 0 here, but it actually retains the original index. So this index column here, it's not really a column, but the index for the rows stays the same as in the original data set. That can be really convenient when you want to rejoin that data, for example, with the original data set, but it can also be a pitfall, so you should be aware of it. So it's can reset that also if you want to get rid of it. And finally, let's write each group to a new data set. That was what we set out in the beginning of this section. And I've written that here already because it's just so super simple that it's almost embarrassing. So you can just use again what we just did, this for key and group in the group data. Or let's write the whole thing. Let's put here also the group by function still, so to see what's the entire code for splitting this file into files by class. And then we can just, this group again is a data frame, so we can just say group to file and then an output file name. Did I call it this? What did I call the function up? Sorry for scrolling away. Topographic database, yes. Where were we? So I just want to say again, like to a file, and then call, like, because we are inside this loop, let's still also have a dynamic file name, which is an F string, so we can put the key name inside here, or the key number inside the file name. And this is all. So if I just run this now, then if I now open that, are you still gonna see the code? Yes, kinda. Then we can see how inside this topographic database, there's all of these terrain something files that were written seconds ago that we just created. So like we now have a shapefile for each of the classes. And it took, yeah, 1.5 lines of code. So it's super convenient. We're not going to go over this extra part down here. It's a very small and short piece, but you will need it for the exercise. So maybe you want to revisit the file and just check out the extra things at home. There's like something missing from these notebooks here, which I seemingly forgot to copy, but we can just go over it on the course page. And is map projections. There's a bit of a long text explaining what map projections actually are, and then what the psychology behind it might be, according to this comic artist. So if you like Mercator maps, you actually don't like maps, is kind of the conclusion here. And yeah, it goes all the way to these really complicated Waterman butterfly things. And apparently the artist hates people who like the Gull-Peters projection, which, as some of you might know, is an attempt of of representing the area of different continents in a better way, so that Europe and US are not overrepresented so much. Anyway, like handling the coordinate system in GeoPandas is super easy. So if we like can only walk through that now, but you can maybe repeat it at home. If you, for example, open this, there's also EU countries in the data directory, and then if you have the geodata frame and you look at its CRS property, that's the coordinate reference system, and it would have everything defined, all the properties of the reference system. So this one is the famous 4326 we talked about before. So WGS datum and latitude, longitude in degrees. And it has a bit more here. So it also tells you, for example, you can use that for the entire world. Yeah, we quickly talked about this EPSG. It's a database, and for example, you can a database of creating these short numbers for difficult projections. So you can use, for example, this spatialreference.org website to see the EPSG definition of, for example, this 4326. So this EPSG is European Petrol Search Group, something like that, something weird. But anyway, people who used GIS in the early days and started to compile a database on these different things. However, there's many other formats, for example, this PROI or this well-known text that kind of mean the same thing. It's just this database makes it into a very short number. And really commonly, you want to change the projection of a data set because you, for example, get this 4326, which works globally, but which is just degrees. So anybody who has looked at Finnish maps knows that Finland is then weirdly, like, I don't know, tilted and distorted, a bit fat actually, like also shorter. It doesn't really look like Finland. So you might want to use like a different projection. And in this data set that is open, that we use in this example, it's like EU countries. Like we could, for example, use this 3035 EPSG code, which is Lambert azimuthal equal area projection, and is the officially recommended projection by the European Commission. And plotting these next to each other, and you might remember this code here, like how to create subplots next to each other, which was in lesson 7 of GeoPython, when you made the different seasons of a data set. You can also use that for plotting multiple maps next to each other, but just to show you, like WGS84 dataset would look like that, and reprojected to the 3035, was it? It would look more like Europe. I only realized this morning that after updating this dataset to the 2022 dataset, has like Great Britain missing. Really weird. But what did I want to show you? Yeah, the reprojection as such is again like this really easy method. So you would use this 2CRS method and then supply some kind of map coordinate reference system definition, and this really accepts a whole range of different things. So I showed you over here that there's these different formats, and there's a long list and like of this well-known text. There's a PROI list. There's different JSON formats. You can pretty much like use anything here. Most convenient usually is if you have a projection that has an EPSG number, to just use that one, because it's just 9 characters and not half a page to type.
We can also make that one available on the Jupyter Lab.
I'm gonna copy that straight away before I leave here. But you will have to restart the notebooks to get the updated version. So if you have it open right now and it's running with the 4 hours, you will have to stop it and run it again. And finally, yeah, you can of course save this again, like use this to file and save it to new file. And underneath that, do we have time to go over that? Yeah, actually time is up. So let's maybe, if you want to know how this works under the hood, it's using this PyPro, PyProi library, and it just can handle all of these different formats of coordinate reference systems, and it can convert between them if you need to somehow figure out how they relate to each other. There's still like a couple of pages in here in this notebook to try out yourself. Finally, there's then this fun exercise of plotting the world in this one that everybody hates, and in different kind of projections. Now quickly still 1 minute concerning the exercise that's due until Thursday the 17th, so in 1.5 weeks. As you already pointed out correctly, this classroom assignment link does not yet work. It's going to work tomorrow morning, promise. But we can already look at the exercise that's already inside this GitHub repository. So it's again 3 problems. Problem 1 gives you 5 points, problem 2, 7, and problem 3, 8 points. It's divided into 3 different files, and I hope it shows here now. The first one is you get a list of longitude coordinates and a list of latitude coordinates, and you're supposed to combine them into 1 polygon. So these, this is the first coordinate pair, this is the second coordinate pair, and so on. And if you put them all together and make a polygon out of that, it's going to show a shape which all of you are going to recognize, I hope, and save that to a geo package file in the end. Works again or tomorrow it's going to work again like last week, that as soon as you push your changes, you're going to get an overview of how many points you already earned. The second exercise is based on real research of Henrik Denkanen, who originally created that course. So he provided us with this CSV spreadsheet that has coordinates, a timestamp, and a user ID of photos that people uploaded to Instagram in Kruger National Park in South Africa. And your task is to load those points from this CSV file, turn them into a geodata file, save them into a shape file, and then still plot them. So I think that was all. So the task is to convert this CSV file into a geodata file, like into a shape file, ultimately, and plot it on the way. And then the third part, which gives you 8 points, is to take this file that we just generated of the Instagram posts of people. It's anonymized, so no worries, but they have a user ID attached, and there's many users that posted more than 1 photo, and we want to find out how far did people travel within Kruger. So the idea is within Kruger National Park, the idea is to take each user in this data set and look at sorted by the timestamp, how far, where did they take the first photo, where did they take the second photos, and so on, and see how long would it take, how long would the line be that connects those different photo locations, to get an idea of how far people traveled. Of course, this is airline, so it's not the distance they actually traveled, but it's a good measure to compare different users. Yes, that's the third problem. So this is using a lot of things that we talked about last week, and then a few things that we did this week. So I think the easier parts of it are actually from this week. So the saving files, opening files, grouping files, and then the more difficult parts, the calculating distances and creating point geometries, for example, or creating polygon geometries are parts that we already did last week and which is a bit of a repetition. Is there anything else to say? I don't think from my side. Do any of you have questions still? If not, thank you very much. Sorry for taking 5 minutes too long, and I hope you have a nice week.